Hello everyone and welcome to Natural Resources Canada's e-training module on implementing deep retrofits. This course has been adapted from the U.S. Department of Energy's Federal Energy Management Program training material on implementing deep retrofits. This training is being delivered through the Natural Resources Canada Greening Government Services to help federal departments and agencies plan and implement projects that reduce the energy use and greenhouse gas emissions in their buildings, laboratories, other facilities, and vehicle fleets. Over the years, Natural Resources Canada has been successfully developing comprehensive methodologies, practices, and tools to reduce energy consumption and greenhouse gas emissions for the private and public sectors, including the federal government. Since 1991, NRCan has provided enhanced technical support to Government of Canada organizations seeking ambitious greenhouse gas emission reduction actions from their building and fleet operations. This training will support federal organizations to meet their commitments and lead by example. Federal facilities have committed to reducing emissions from their operations by 40% below 2005 levels by 2025 and by 90% by 2050. As outlined in the 2020 Greening Government Strategy. This initiative also supports the commitment by Canada's federal, provincial, and territorial First Ministers to scale up efforts to transition to highly efficient buildings and zero-emission vehicle fleets, as specified in the Pan-Canadian Framework on Clean Growth and Climate Change. This course is designed to address a range of core competencies for both energy sustainability managers and facility managers, as well as for operating engineers and building technicians. As a result of completing this training, we hope that you will be able to select appropriate facilities for deep retrofits and set performance objectives, employ an integrated design process, and use technology applications for deep retrofits, determine how you will ensure optimal performance, and identify federal and industry resources to support your decision-making processes. This course is broken down into a number of segments. We're going to start with an overview of deep retrofits and understanding deep retrofits in general. Then we'll go over the process for deep retrofits, integrative design, financing, and utility markets, end-use technologies, ensuring optimum performance, and we'll end with a few case studies. We're going to start by going over defining what a deep retrofit is. Natural Resources Canada has identified 3 categories of energy retrofits that we will go over now. The first category is a minor energy retrofit. These projects typically involve a single measure or a focused group of measures that result in savings of up to 15%. Minor energy retrofits involve low-cost measures that are easy and inexpensive to carry out, but can make a considerable difference to the facility's energy consumption. Some examples include lighting upgrades, caulking windows, and modifying operational schedules. These measures often have quick payback periods. Cons of this approach are that they have limited energy savings and may exhaust low-hanging fruit. That is, energy-saving measures that have a quick payback and that might otherwise help fund longer payback measures. The second category is major energy retrofits. These retrofits are generally more holistic, involving several measures across multiple building systems and lead to savings between 15% and 40%. Implementation of these measures should typically be staged to maximize energy savings. These projects are often done through an energy service company, or ESCO. You would typically see measures like lighting, HVAC equipment, and controls. They are higher in cost and usually have a mechanical focus. Major energy retrofits have higher upfront costs, but these retrofits can often obtain financing given their strong financial case. Finally, there are deep energy retrofits, which we'll be discussing in more detail today. For deep energy retrofits, savings can be greater than 40% because they take a comprehensive view of all the building's energy-using systems and involve significant overhauls to major building systems. Due to their disruptive and cost-intensive nature, they are usually triggered by non-energy-related factors such as the end of service life of a major component or a significant change in building occupancy. Deep retrofits are almost always done along with other capital improvements and take an integrative approach to finding solutions. Instead of looking at a single renewable energy project or looking at one mechanical system, this type of project would take a comprehensive view of the building and look at how each energy efficiency measure can impact the building, the occupants, and the value of the property. Although deep retrofits have a high upfront cost, making such big changes to the facility can lead to substantial savings that make the project extremely cost-effective, paying itself off within a reasonable time frame. Since deep retrofits take such a broad view of the building and its systems, they require much more coordinated planning to execute. Deep retrofits also require more advanced financial planning, often being done through a capital expenditure plan or through an energy performance contract. How is a deep retrofit project different from other retrofit projects? Well, there are several differentiators. The first and biggest differentiator is that deep retrofits require a broader conversation with the facility owners. You will be much more involved with the owner's motivation and the owner's real goals, aside from their energy targets. It's also a very integrative design process from start to finish. It should include everybody involved in the project. Integrative design leads to innovation, and you'll see a much higher level of innovation if everyone is able to contribute their ideas. Deep retrofits also include advanced energy modeling and life cycle cost assessments, or LCCAs. Advanced energy modeling is not a deliverable, it is a process. The energy model is used to help make decisions, to help form the building itself. Modeling should be used from the beginning of the project by starting with a conceptual model and going forward from there. Energy modeling is incredibly powerful, so it's important to find people who know how to do it well. The next factor is that there's ongoing energy tracking to provide proof of success. This wouldn't just be a checklist once a year to see if all the set points are still where they're supposed to be. This would involve measurement and tracking, real-time energy tracking to assess how the buildings are performing. Deep retrofits take a holistic approach to energy efficiency through a comprehensive retrofit process and a long-term approach. The ESCOs involved are also interested in creating long-term relationships with their clients. Deep retrofits follow a differential model. You have to think about the tenants when developing your energy reduction strategy. The tenants are essential in these projects. For example, deep retrofits look at plug load issues such as energy use from computers. So it's important to get the tenants on board with reducing energy. Finally, for deep retrofits, timing is key. Deep retrofits must take into consideration timing of other planned renovations. These differentiators lead to larger savings and improved project economics every time. You will always get deeper savings if you follow these concepts. Retrofit targets are outlined in ASHRAE's Standard 100, Energy Efficiency in Existing Buildings, which provides the minimum energy efficiency requirements in design and operation of existing residential, commercial, institutional, and industrial buildings. This standard provides energy use intensity, or EUI, targets for 53 different building types in 16 different climate zones. You could use this value as your maximum target. However, if you really want to see improvement savings, you should set your EUI target based on the top performing facilities in the 25th percentile. In this next segment, we will discuss the process for implementing a deep retrofit. The process for a deep retrofit is more akin to that of a standard design project rather than that of a standard retrofit. This slide shows the 4 stages of the process. First, there's the launch stage. At the launch of the project, you should set goals, and your goals should not be limited to energy targets. You should ask yourself, what does the owner want to get out of this project? What is the department trying to accomplish through this project? What other market factors are at work? Are they worried about losing their tenants? Is there something going on that could cause the building to change function? For example, the goal could be to accommodate a growing workforce. That doesn't necessarily mean you need more offices. It could just be that the building needs to find an innovative approach to accommodate a growing workforce. Office spaces are changing quickly due to technology advancing. How can you design 21st century workplaces and make them more energy efficient? Those goals are important, and the owner will set those goals with our help. Next, you'll need to select a team consisting of design engineers and architects. Then it's important to establish the baseline, gather data, and model a business as usual scenario. When you get into the design aspect of a deep energy retrofit, You need to identify opportunities right from the start. A good approach is to have a charrette or a design workshop, and these design opportunities come through a collaborative meeting. It's important to invite the entire team to these meetings and encourage everyone to share their ideas. During these meetings, it's best to have an open mind to any idea that's brought up. Then, analyze the options. There's a lot of analysis required in deep energy retrofit, and you'll often be working side by side with the architects and engineers. The analysis is iterative and recursive process. Design is not a linear process. You often have to go back and change things and add new ideas. The next step is to implement the project. This involves construction, followed by commissioning of the project. The final step is verification, which is very important. Measurement and verification is often used, but now we are seeing trends towards the measurement and tracking. Verification is often just done once a year. Measurement and tracking, on the other hand, is ongoing, so if something goes wrong with the system, you can catch it right away. And then finally, share successes. If your project is successful, let others know about it. Within the realm of deep energy retrofits, we talk about the concept of ripeness, the suitable timing of a deep retrofit. Ripeness can depend on a number of factors. If the building is due for an upgrade and hasn't been touched in 20 or 30 years, and there are planned capital improvements, then the time is probably right to do something deeper. You need to have mechanisms within your acquisitions process, your capital planning process, to account for energy efficiency improvements in the form of a deep retrofit. Then there are major system replacements. If you're going to replace major equipment, you should also try to reduce the loads that those systems need to meet. If you can invest more money into the building envelope and the passive measures of the building to reduce the load itself, then those major system replacements will often change scope. This is part of the integrative design process where you look at the whole building before you look at individual systems. Next, there may be major envelope projects. When you look at mid-century modern buildings, envelopes are tough. Sometimes they can be rebuilt, but other times they just have to be replaced. It depends on how they were constructed. That's a major project and a major opportunity for improving the envelope of a building that can really reduce the building's energy loads. So take advantage of that. If energy is not part of those larger envelope projects, you're missing something. There may need to be changes based on code upgrades. It's tough to keep up with the codes right now since they're moving so fast, but taking advantage of them whenever you can as part of the upgrades is important. If there's a new owner, opportunities for refinancing or a new use or occupancy type is appropriate. If the building is really changing in character, that is a great time to step in and implement a retrofit. Then there might be the opportunity for large utility incentives, and if there are high energy costs, that's a great motivator as well. Then there's mitigating an energy hog. Some old buildings have been allowed to deteriorate to a point where they're using an enormous amount of energy. Often it's old solutions that have caused the problem, so there's an opportunity to go back and recover the energy efficient aspects of the buildings. Ultimately, we need to talk about this from a portfolio management perspective. If you're working with a department or a client that has a large group of buildings, they are managing this portfolio like a juggler would manage balls. There's a lot up in the air. They're looking at many aspects of portfolio management, what to keep, what to dispense of, how to upgrade their buildings so that the energy doesn't get away. You're looking at enormous costs of energy in some of these portfolios, and they know that that's a real opportunity. There are many potential barriers to deep retrofits. Policy is an obvious one. There can sometimes be a lack of policy to create motivation to invest in capital projects. There are many ways to find creative alternatives to financing and figuring out this barrier. The policies to allow deep retrofits and to encourage deep retrofits can sometimes get in the way, but they can also be very helpful. The Federal Sustainable Development Strategies and Pan-Canadian Framework are policy instruments that encourage deep retrofits. The improving performance trends of energy codes are also moving at a very rapid pace. Policies in that respect are pushing for better performing buildings. Since the energy codes are moving so rapidly, you cannot rely on just mechanical system upgrades. You'll have to turn to holistic, deep energy retrofit solutions to meet those codes. Then there are project analysis tools that could represent another barrier. These tools are still being developed. There's a workforce of service providers out there who may or may not know those systems. When you go out looking for an energy modeler, you'll want to find someone competent and experienced. Not all energy models will have this level of expertise. If you are an energy modeler, or if you are a service provider, training is very important to keep up with the rapid advancement of these tools. Then there's the uncertainty of technical and economic performance. For many new conservation measures or energy-efficient measures, you don't really know what the outcomes could be, what the savings could be. Again, it's based on sometimes limited or no energy modeling. So what can we do to tighten up the information we have and the data that we have? If you really want to be innovative, sometimes you don't know what the savings will be. There are workarounds. You have to get creative and you have to reduce risk. Getting access to capital funding can be a problem, although there may be other options to receive external financing. Third-party financing can be received through banks, trust companies, credit unions, and other private financing companies. For large energy retrofit projects, there's also the option of using the energy performance contracting. This option is attractive because it does not require in-house energy management expertise, and all risk can be transferred to the Energy Service Company, or ESCO. In this next segment, we'll talk about optimizing the building and the process. This slide shows the deep retrofit right steps in the right order. The first step is to define your needs and set your goals. We talked about defining goals and setting goals right from the start. Then you want to understand the existing building. What's there? What is the capacity of that site? How much renewable energy could you possibly generate on that site? Water is becoming a bigger issue too. What is the capacity for waste on that site? Now you have to understand the existing building operations. You should know what the baseline is, and you should know what the cost of doing nothing is. It's incredibly powerful to know what the cost of doing nothing is, because that helps define your budget. If you can reduce that budget further, that's also good. Then you want to understand the scope of the planned renovations. What is the plan? What is the purpose of the renovation? What is the motivation behind this project? That way, you can merge your project with some of the larger ideas. You can develop synergies between what you're trying to accomplish and what the renovation project's motivation is. Then, you want to reduce loads. What should be first and foremost when you start talking about technologies? What loads can you reduce in the building to eliminate entire systems or partial systems? You want to reduce as much as possible without compromising comfort. Simplifying these loads is a huge opportunity to declutter these buildings. Now, some people start at this next step. You want to select appropriate and efficient technologies, but only after you've reduced the loads and after you've understood the scope of the project and after you've determined the cost of doing nothing. Do your homework first, then look at the energy-efficient technologies that are out there. Then you want to seek synergies. A lot of systems, a lot of energy conservation measures or energy efficiency measures have terrific synergy. They can complement each other to reach even greater energy savings. There are a lot of things that can be done for a building that add up to more than just energy cost savings and more than just aesthetic improvements. Keep in mind all these things. Don't discount anything. Even the small improvements add up. Keep in mind bundling these measures so that you can get a larger impact. Then you want to optimize controls. Controls are very important, even if the building occupants have good intentions. If you want to see energy savings, you have to have a lot of control over the building. The building needs to be automated and it needs to be recommissioned constantly. And then after all these steps are completed, you can integrate renewable energy. Renewables should be the very last step. When you're done with a good project, renewables are the cherry on the top that help achieve even greater savings. Ultimately, you need to realize the intended design. Make sure the project is going to perform the way it's supposed to perform as designed. Then commission the building and continue to recommission at regular intervals. Commissioning the building is crucial to ensure that it operates in the way it was designed to. Now we're going to go over the processes to estimate the achievable potential of a project. You start by calculating the minimum technical potential. What's the lowest energy use you could theoretically achieve? You would start with a building's current energy use and then remove all the constraints that are negatively affecting its performance. This includes physical constraints, economic constraints, everything that could be impacting the building's performance. Input this into your energy model to get the technical potential. Your long-term goal should be to reach the technical potential. Unfortunately, reaching the technical potential is rarely feasible, so you have to add constraints back in. Constraints can be due to codes, budget resources, etc. Adding back those constraints, you end up with an achievable potential. The achievable potential is your short-term goal. You could end up at a very different end goal by following this path than you would by starting with existing energy use and then deciding on an arbitrary savings value. Whenever you go through this exercise on a project, you end up with much better performance than if you started at the top and worked your way down. This way, you're starting at the bottom, you're justifying every gigajoule that's expended, and you know where it's going. The aim should be to optimize the whole project, not the individual parts. There's no point in going into a building and just fixing one aspect of the building and not addressing anything else. A building, like any other system, is a sum of parts as a whole, and you need to look for holistic solutions. That's why we're talking about early intervention, goal setting, and technical potential. This helps you look at the building as a holistic problem with a holistic solution. In this next segment, we're going to look at financing and utility markets. Factors for economic success in a deep energy retrofit vary. We've talked about facility selection already. Not every building is ripe for a deep energy retrofit right now, but there may come a time when it will be. If there are several buildings in your portfolio, you need to determine which ones are ready for an energy audit, recommissioning, or an ESCO project. Then you need to identify which buildings are ready for a deep retrofit. The more you can reinvest the savings from energy projects into a future deep retrofit, the better. The cost of energy varies depending on where your jurisdiction might be. There are some parts of the country where energy is very expensive, and the energy costs themselves can be a huge motivation for the project. Another factor is the owner's motivation. Why is the owner motivated to do this? Are they getting ready to sell the building? In addition to costs, another motivating factor for federal government facilities is the potential for GHG reductions, especially in provinces with dirty electricity grids. Finally, there's the question of financing strategy. There are many different financing options available to most clients, whether they're private or federal. You need to get creative there as well. Quite often in a traditional project, you will invest in energy efficiency until you meet what is perceived as a cost-effective limit. And then you'll stop because you're spending as much as you're going to save. So this will be the cost barrier. What happens if you keep spending and pass the perceived cost barrier? If you keep going, you could ultimately eliminate entire systems, in which case your costs would drop tremendously. Next, we're going to go over the role of energy modeling in integrative design. Energy modeling is fundamental to a deep retrofit process. Most retrofit projects use spreadsheet-based models. Moving to more of an integrative process, where we're using energy modeling as a fundamental step in the right direction. There are many software tools available, and we're going to go through a few of the available ones. The first one we're going to talk about is called RETScreen, the world's leading clean energy project analysis software. RETScreen allows energy professionals and decision makers to identify, assess, and optimize the technical and financial viability of clean energy projects. The newest version of the software, RETScreen Expert, models a full range of both traditional and non-traditional sources of clean energy, as well as conventional energy sources and technologies, including energy efficiency, heating and cooling, power, and combined heat and power. RETScreen is managed under the leadership and financial support of the CanMet Energy Varennes Research Centre of Natural Resources Canada. eQuest is another commercially available software tool that you can use. This modeling tool has a detailed description of the thermal properties, so the building envelope, the internal loads, the lighting, and the HVAC systems, and all are again really taking into account these integrative effects of layering on these different opportunities that we're talking about. The final energy modeling tool that we wanted to go over is a tool called Open Studio. This tool was built with funding through the Department of Energy's Building Technologies program and is the first open source tool for modeling in Energy Plus. It has a Google SketchUp front end. It allows you to go all through the building and energy model. One of the features included in this tool will have what's called a building component library, which allows the energy modeling community to build components and keep them in an open source environment where other energy modelers can use them. If you create a chiller, for example, you can take that chiller that you've created and other people can use that later on. It's a really neat way for people to build systems that can easily be used and shared with other energy modelers. There are other software tools out there, and the main takeaway is that you need to be performing energy modeling as a part of this process. So, ensuring persistent savings. You should also energy model programs to identify effective energy conservation measures, or ECMs. You should make sure you're commissioning the measures that you're implementing. Commissioning is an important process in order to secure the success of the project. There are numerous measures that are going to be found within a commissioning effort that aren't working correctly, so a third-party commissioning agent is critical to making sure that those are caught and captured. You should also make sure that you're following up with correct operational and maintenance protocols, and as mentioned earlier, it's important to implement measurement and tracking. One of the most useful things that energy modeling can provide is an indication of how much energy should be consumed in end-use systems. If you're measuring your lighting system, for example, you know how much energy your lighting system should use, and you can compare that to your model loads and see how well that model is comparing to your energy use over time. So measurement and tracking are critical. In this next segment, we'll go over end-use technologies. There are hundreds of technologies that we could talk about today, but given the limited time we have, we're going to focus the discussion on integrating these technologies into a deep retrofit project. There are several technologies that might not be mentioned that could, of course, still be implemented in deep retrofit projects. But what we're focused on is giving you an idea of how this process is different than a standard retrofit, and then how these items get integrated into a deep retrofit. Let's start with the building envelope. The building envelope can be one of the most expensive systems to retrofit, and the energy savings associated with it are a function of the building size. The smaller facilities are going to see greater energy savings per square meter from building envelope retrofits than the larger facilities. There are also many other factors that can drive envelope retrofits besides energy savings. For example, there could be thermal comfort complaints because of single-pane windows and leaky walls, another reason you might need to upgrade the building envelope, and this can give you a segue to use that opportunity to start on a deep retrofit. For building envelope opportunities, standard retrofit items are going to include things like adding roof insulation, adding a cool roof, air sealing, and blown-in wall insulation. When you move to a deep retrofit, what you're doing is optimizing these systems to include passive opportunities, as well as upgrading the thermal performance of the building envelope itself. For example, you would take into consideration how daylighting is going to play into the building. Often, when a building envelope is retrofitted, daylighting is given little to no consideration. You also want to make sure that you're thinking through the process of selecting an appropriate glazing type, depending on which building envelope system you're retrofitting. There are also the standard items like roof insulation, wall insulation, and upgrading the windows. For building envelope upgrades, roof retrofits are the most common retrofit because roofs need to be replaced regularly. Planned replacement is a great time to add insulation and retrofit them in an energy-efficient way. When you're doing a roof retrofit, there are a few starting points you can consider. One of those starting points is going to be set to a minimum R value based on ASHRAE standard 90.1 and a target R value. As you can see, there are very aggressive insulation requirements. Reaching R50 to R60 would require a lot of insulation in the roof, either as an exterior foam board or an interior insulation. So you should use this target as a starting point and fine-tune this number based on any limitations you have with your existing building construction or the building location. Here's where an energy modeling program can help make sure you're aiming for an appropriate R value target. The R value should be determined through an iterative build and modeling process. Some other options to consider would be a cool roof, like a low absorptance white roof or a green roof. Green roofs have several benefits relating to reducing heat island effect and reducing runoff. Wall retrofits are some of the trickiest measures to implement. They are one of the more expensive retrofits in commercial buildings. There are often challenges with wall retrofits in historic structures. You'll need to look at the new dew point of the wall and how the airflow is going to move through that wall. Wall retrofits are some of the trickier measures, but crucial to ensuring thermal comfort within the assembly. Finally, there are window retrofits. There are 3 retrofit options that you should consider when moving forward with a window retrofit. In all cases, you don't want to have to replace the entire window. One of the options is to put in an interior blast window, which essentially acts as a double-pane window and which improves the performance of the window. You can also refurbish the window. There are many ways of doing this. One option is to add a mylar film to the window, increasing its R value. You can achieve really good R values with this method, and the cost threshold is lower than that of a new window. Finally, there's the option of installing a new window. If you choose to install a new window, you'd want to set aggressive performance targets. If you install new windows, there are options such as going from double to triple glaze, low E-coatings, and insulated frames. So to recap, for the building envelope, it's important to address the walls, the windows, and the roof, and as you're doing those, you should address air sealing within the facility. As you're addressing those window retrofits, make sure that you're putting in the appropriate windows to make use of daylighting, and also make sure that they're sealed appropriately so that you can implement other types of HVAC projects that we'll talk about here in a minute. Next, we'll talk about lighting, one of the most common retrofit items within facilities. Standard retrofits are going to do things like retrofit existing fixtures, in which you change out the lamps and ballasts. We can put in occupancy sensors, replace exit signs. These are all common items you will see implemented within a standard retrofit. As you move into a deep retrofit, you'll be taking a fundamentally different approach to lighting. The first step is to make sure that you're determining the visual needs of the occupants. You need to make sure that you're hitting the appropriate illuminance levels within the space. After you've done that, you need to determine an optimal lighting solution for that space. For example, you should move towards using a lighting power density metric to determine the appropriate fixture type to meet a specific watt per square meter threshold that you want to hit. After you've done that, you'll layer on daylighting controls and then other advanced controls such as vacancy sensors and occupancy sensors. These measures work together to change the lighting energy use within a facility in a more holistic and comprehensive way. Let's start with daylighting. Daylighting can be very important in optimizing your lighting systems, and it's challenging to do it correctly. You'll often see facilities that have implemented daylighting strategies incorrectly. One of the most common mistakes is putting in daylighting controls, but then having no way of controlling direct sun in the windows. So the occupants will close the blinds, and then the daylighting controls don't do anything. So the first step in correcting using daylighting is to make sure that you have redirective devices that are controlling glare in the space and allowing direct sunlight in at some level. On this slide, we're showing a simple graphic of some redirection blinds. The way these work is the upper portion of the blinds allow for natural daylighting to bounce into the space, and the lower portion of the blinds can be closed by the occupants so that the light is blocked. This is a solution where you'll always allow daylighting into the space, even if the occupant closes the blinds. Another option is a light shelf, which allows you to redirect the light into the space. Again, you should make sure that you're maintaining a visual connection to the outside. It's harder to put in appropriate glare control in existing buildings than in new facilities. You need to look at each facility to determine an appropriate solution. The lighting redesign requires consideration. What the designer needs to do is find the appropriate illuminance levels for a space and then set the lighting power density to achieve those levels most efficiently. The lighting power density is the watts per square meter that we want to achieve for that space. Both the illuminance and the lighting power density should be considered upper limits. For example, in an open office with a recommended illuminance of 323 to 538 lumens per square meter, it's better to hit an illuminance target closer to 323 lumens per square meter and to reach that target with a combination of overhead and task lighting. It's the same for lighting power density. We have listed here a lighting power density of 9.7 watts per square meter for offices. There's no reason that you can't hit a target of 6 to 7 watts per square meter within these facilities. With some of the new lighting technologies, you can see designs even below 5 watts per square meter. So there's opportunities to drastically reduce energy usage. Here is a case study to illustrate the impact of lighting redesign considerations. On the left-hand side, there's an image of a traditional layout of an older facility. Facilities built before we had computers, so any facility before 1970, were designed for drastically different illuminance levels. The example on the left has an illuminance level of 967 lumens per square meter. You can see that in this design, 20 light fixtures are required to meet the required illuminance level. So if you're trying to retrofit that facility, you're stuck with all those light fixtures, and traditionally what was done is to simply change out the lamps and ballasts in each fixture. On the other hand, if you have an opportunity to redesign that space, you can get rid of a bunch of those light fixtures and put in more efficient lighting fixtures. This will drastically reduce your energy usage. Here, for example, you can see that the facility has gone from 20 fixtures on the left to 9 fixtures on the right just by setting an appropriate illuminance target and putting in a more efficient lighting fixture system. This allows the building to hit a more lower threshold for power density, that is watts per square meter. That's what you want to do, to redesign the space, get in the appropriate light fixtures, and then layer those with appropriate daylighting controls, occupancy sensor controls, and vacancy sensor controls. Plug loads are one of the more challenging end uses to implement measures. Once you've implemented a building envelope measure, it's typically persistent for 30 to 50 years. Lighting measures are also fairly static in relative terms. Plug loads, on the other hand, are controlled to a great degree by the occupants, making it challenging to predictably regulate those loads over the long term. On this slide, standard retrofit items are listed on the left. There are things that are typically done, such as changing desktop computers to laptops, computer power management, and LED monitors. When it comes to a deep retrofit, what we're doing is similar to what we've just presented through lighting. We're talking a different approach to reducing loads by setting either a power density requirement or workstation allowance. A workstation allowance would only allow so many watts per person, which is drastically different than the current approach, which allows unregulated watts per square foot or watts per person. Then you could add advanced controls. There are many plug load controls available, such as schedule timers, load sensing plug strips, which sense the loads on that plug strip and turn them off or on into a low power state, and occupancy sensor controls. For plug loads, the industry is changing quickly, and there's a lot of innovation happening that's allowing us to achieve much lower plug load targets than was possible just a couple of years ago. If you're aiming for a power density or a workstation allowance, we've provided 2 examples that you can use as starting points here. Looking at power density, you could aim for 6 watts per square meter, which is 50% above ASHRAE's standard 90.1 2010. Another option is to aim for watts per workstation target. For example, we're listing 60 watts per workstation, which is a huge difference between how we operated our plug loads a long time ago, even just as recently as 10 to 15 years ago. If you take a look at this example workstation, there is a combination LED LCD monitor, LED task lighting instead of linear fluorescent task lighting, a lower energy use computer, and you are being cognizant of residual loads such as a phone load. These lead to significant decreases in energy use. If you compare this to a workstation from the mid-90s, the monitor alone would use over 100 watts, the computer would use over 100 watts, and the task lighting would be in the 30 to 60 watt range. You'd have 300 watts per workstation compared to the 60 watts or less workstation that we have here. For plug loads, there have been huge advancements in computing energy use recently. Most big computer manufacturers pay close attention to energy usage and offer low energy options that allow you to provide very efficient computers for your employees. For example, a standard desktop computer uses between 80 to 100 watts. Now there are computers available that have the same processing power but use considerably less energy. We're seeing lower and lower energy usage with ever better processing and memory power. Looking for Energy Star certified computers ensures that the model you select will deliver substantial savings over standard models. To get an Energy Star certification, desktops and notebook computers must meet stringent TEC, or typical energy consumption, requirements for their estimated annual energy consumption. You can look on the Energy Star website to find a full list of certified models. Behavioral change is an important factor in reducing plug loads. There are a few ways to promote behavioral change. One way is to submeter plug loads so you can receive real-time feedback on how much plug load energy you're using. You can do weekly prompting or have an occupant competition. What you want to do is layer these strategies with controls. You want to make sure that you have plug load controls in place that are regulating usage and not just leaving it up to the tenant to regulate themselves. Now, we've talked through the first three items: building envelope, plug loads, and lighting systems. Those systems should all be implemented before you look at HVAC considerations. You want to reduce your loads as much as possible, and it's not unusual to reduce your loads as much as 50% before addressing your HVAC system. Since most HVAC systems are oversized, it's not uncommon to put in new HVAC equipment that's less than half the capacity of what was there before. So as a first step, you should reduce your loads, and the second step is to implement efficient HVAC systems to serve those loads. Standard retrofit items include converting constant volume pumping to variable speed pumping, putting in variable frequency drives, and HVAC controls. Deep retrofits take an innovative approach to either setting a performance reduction target or fundamentally changing the HVAC system that was there before. Some examples include converting constant volume to variable air volume, downsizing the equipment that you're putting in, and then these last four are innovative ways that HVAC systems are being implemented in new ways that haven't been seen in the past 30 years. There's dedicated outside air with energy recovery. If you put energy recovery on outside air ventilation, you can reduce your ventilation loads by 50%. Installing heat pumps is a huge way to reduce energy usage. Then there's radiant heating and cooling that allows you to provide heating and cooling to the facility with much lower energy use than standard forced air systems. To be innovative, you can apply a combination of these strategies into a deep retrofit. Finally, we're going to talk about controls. We use controls to integrate all our energy systems. We're integrating with HVAC, with lighting, and with plug loads, and making sure that those are all working to control the building properly. The last thing we're going to discuss is renewable energy. Once you've optimized your energy use at your facility, the last step is to install renewable energy to meet your newly reduced loads. Renewables should be sized at the end of the process as a function of the new reduced load. They should take into consideration the building type, the renovation type, and the historic preservation of the building. As you're retrofitting a system, you want to look at these renewable energy options. There are several renewable energy options that should be considered and potentially implemented into your facility. Now we're going to go over some case studies of deep retrofit projects that have been completed or are underway in Canada. The Ontario Association of Architects, the OAA, decided to proceed with a deep retrofit of their headquarters in Toronto, Ontario. As the building passed its 20-year mark, it became apparent that the maintenance costs and energy use of the building were significantly above average. Several options were considered, including moving locations or rebuilding the facilities from scratch. In the end, it was determined that it would be economically feasible to proceed with a deep retrofit project. The OAA wants to get ahead of the curve with their energy reduction targets by aiming for a net zero building. The first step in the building retrofit will be envelope upgrades to reduce the heating and cooling loads. According to blower door tests, the OAA building envelope scores very well for air tightness, but insulation can be added to further reduce the loads. Next, the team looked at the mechanical systems. The current mechanical system uses forced air heating augmented with reheat coils in each variable air volume or VAV box, and electric baseboard heaters. In cooling mode, the system cools air and then reheats it for each individual office. While this strategy was considered good when the building was built, it consumes a lot of energy. Also, after 20 years of service, many of its components are coming to the end of their life expectancy. The OAA is proposing to entirely rework the mechanical system, changing it to a displacement system and adding an energy recovery ventilator. The building also has fantastic daylighting that is currently duplicated with artificial lighting. They have designed a system which will replace existing lighting with high-efficiency lighting using a daylight strategy to turn off lighting when sufficient daylight exists. Finally, the system will be driven by photovoltaics with an integral hydrothermal system, made more efficient through the use of underground storage tanks to both store heat and absorb heat from the ground. Another example of a deep retrofit project is the Belmont Condo in Vancouver. Built in 1986, the 13-story building has deteriorating assemblies and needs renewal work. The energy efficiency upgrades were only one part of the building renewal project that also involved improving the comfort, durability, acoustics, and aesthetics. One of the most effective energy efficiency upgrades was on the building's envelope, starting with the wall. The existing exterior walls were exposed cladding with 50 millimeters of foam insulation having an R value of R4. For the renewals project, the walls were overclad with 89 millimeters of mineral wool insulation behind stucco and metal panel cladding. This assembly resulted in an R value of R16 for the exterior walls. Upgrades were also made to the windows. The existing windows were double glazed with air fill and no-low E coatings in non-thermally broken aluminum frames. These were replaced with triple glazed windows with fiberglass frames, improving the window U value from U.55 to U.17. Finally, air tightness improvements were made to the enclosure through installation of a liquid-applied air and water barrier over cracks in the concrete. The whole building air tightness was tested before and after the retrofit. The initial pre-retrofit air tightness was 7.6 CFM per square meter at 75 pascals. Following the retrofit, the air tightness dropped to 3.5 CFM per square meter at 75 pascals. This project was completed in 2012, and results of measurement and verification show that this retrofit has been cost-effective for the building owners, with an improved EUI of 0.63 gigajoules per square meter compared to the baseline of 0.80 gigajoules per square meter and a simple payback period of 2 years. A second phase of the project is currently underway to increase energy savings even further. The final case study that we'll be going over today is the Place de Portage in Gatineau, Quebec. We've talked a bit about using energy performance contracting, or EPCs, as an alternative financing option. Public Services and Procurement Canada was an early adopter of EPCs. This low-risk, alternative form of financing is available for energy retrofit projects that operate through Natural Resources Canada's Federal Buildings Initiative and enables organizations to carry out major retrofit projects without the upfront costs. One benefit of EPCs is that they are flexible, which was a huge benefit to PSPC. Using EPCs, you can adjust the project to a degree and respond to additional energy savings and related capital renewal opportunities as they present themselves. In this case, the team was able to modify the scope midway through the project to respond to changing conditions. Place de Portage Phase 4 has a floor area of more than 86,200 square meters. Before the energy retrofit, it had unusually high energy consumption for an office building of its size, prompting PSPC to implement an EPC project. After a competitive bidding process, the contract was awarded to Amerisco Incorporated, an energy service company qualified under the FBI's qualified bidders list. The scope of the project initially included modifications to the HVAC system, control system upgrades, lighting retrofits, an upgrade and refurbishment of the cooling towers, and replacement of one of the facility's 3 chillers with a modern, efficient machine. Portage 4 was built with constant volume, dual-duct HVAC systems throughout the building. The entire system was converted from constant volume to variable air volume by installing variable frequency drives on the supply and return fans and individual VAV box controls. The system now varies the volume of air to maintain zone temperature, which reduces electrical power requirements and eliminates simultaneous heating and cooling. The building automation system was also upgraded to a more efficient control system. The system's functionality was expanded, including extending BAS controls to the individual VAV box level and control upgrades to better utilize the facility's existing electric boilers. The new automation system also includes a fully integrated building lighting control system. Lighting retrofits achieved savings by decreasing the number of lamps and fixtures and by improving fixture design and technology. For example, corridor spaces had ample light fixtures, but the light distribution was uneven, and much of the corridor space was not well lit. All the fixtures were replaced with modern fixtures that optimized light dispersion. This measure decreased the number of light fixtures while simultaneously providing improved, uniform lighting levels throughout these areas. These upgrades and the flexibility of the EPC financing option allowed the Place de Potage building to see significant energy savings, optimized building operation, and improved occupant satisfaction. In an effort to help the federal government reach its greenhouse gas emissions reductions, the Real Property Institute of Canada has offered energy efficiency awards for federal buildings. The RPIC is a not-for-profit organization which supports the federal real property community in Canada in professional development, recognition, and advocacy. The Excellence Award for Energy Efficiency of Federal Buildings recognizes projects that have achieved a significant reduction in energy consumption, reduction of greenhouse gases, and improvement of the work environment. There are also several tools and resources available online. Natural Resources Canada has a guide on major energy retrofits for commercial and institutional buildings. ASHRAE also has advanced energy design guides that can be used for projects that achieve 30 to 50% energy savings. Now, we will have 10 quiz questions to test what we've learned. Question 1. Which of the following would present a key opportunity to complete a cost-effective deep retrofit? A. Roof window or siding replacement. B. End of life cycle for major equipment such as HVAC. C. Required upgrades to meet code. D. Occupancy or mission change for the facility. Or E. All of the above. The answer to question 1 is E. All of the above. Question 2. Using the analytical process involved in deep retrofits, consider the following scenario. The roof is slated for replacement in 5 years, but the HVAC is close to the end of its life cycle. It makes the greatest economic sense to A. Continue with the existing HVAC for 5 years and then add insulation and consider green roof options at the same time you replace the HVAC. B. Replace the HVAC now but add insulation to the roof in 5 years. C. Replace the HVAC and the roof at the same time so that the size of the HVAC unit needed to heat and cool the space can be reduced. D. All of the above should be considered. Or E. None of the above. The answer to question 2 is C. Replace the HVAC and the roof at the same time so that the size of the HVAC unit needed to heat and cool the space can be reduced. Question 3. A key consideration in deep retrofits is to reduce building loads. Choose the option that best represents the logic of deep retrofits. A. Employ passive means to reduce loads first and then specify the most efficient equipment. B. Begin with a high-efficiency choice in HVAC and then consider other load reduction measures. C. Specify the most efficient non-HVAC equipment replacements and then consider the HVAC system. D. A and C above. And E. None of the above. The answer to question 3 is A. Employ passive means to reduce loads first and then specify the most efficient equipment. Question 4. The relationship between commissioning and deep retrofits is A. Deep retrofits replace the commissioning process. B. Commission the building prior to considering deep retrofits. C. Commission the building after implementing deep retrofits. D. Commission the building before and on a continuous cycle after a deep retrofit. Or E. None of the above. The answer to question 4 is D. Commission the building before and on a continuous cycle after a deep retrofit. Question 5. A comprehensive lighting retrofit should result in A. A dramatically more appealing space. B, an improved visual environment that meets the needs of occupants. C, significant energy savings. D, incorporating natural daylighting with controls that will in turn reduce cooling loads. Or E, all of the above. The answer to question 5 is E, all of the above. Question 6. Deep retrofits generally look to the following as the first choice of a lighting upgrade. A, addition of solid-state lighting. B, addition of task lighting. C, daylighting. D, spectrally enhanced lighting. Or E, none of the above. The answer to question 6 is C, daylighting. Question 7. Which of the following systems is an important component of a deep retrofit which is generally not a component of a standard retrofit? A, building envelope. B, plug loads. C, lighting retrofits. D, education of building occupants. Or E, none of the above. The answer to question 7 is A, building envelope. Question 8. The largest source of excess energy consumption attributable to the building envelope is A, air infiltration. B, solar radiation. C, inadequate thermal insulation. D, roofing materials. E, none of the above. The answer to question 8 is A, air infiltration. Question 9. The range of temperatures during which no heating or cooling takes place at the zone is referred to as A, load range. B, zone peak. C, deadband. D, comfort range. Or E, none of the above. The answer to question 9 is C, deadband. Question 10. A key strategy for being able to downsize mechanical equipment in a deep retrofit is to A, install more efficient duct and piping layouts. B, minimize building loads. C, address building envelope issues. D, improve lighting efficiency. Or E, all of the above. The answer to question 10 is E, all of the above. Here is our contact information if you have any questions concerning deep retrofits. Thank you for participating.